Okay, so what we're having a chat about today is like the difference between what we expected from wave theory and what we actually got when we did the photoelectric effect experiment. Because there were some pretty clear expectations, and the reason that the whole model had to be thrown up in the air and redesigned is because the expectations didn't match the results at all. So, first of all, intensity of light. What do we mean by intensity of light? In a wave theory, we'd expect like brighter light to be like greater amplitude light. What effect might we expect that to have on the energy transmitted to electrons in metal? More energy. More energy. What was the actual result though? What do we find when we turned up the intensity of the light? On our experiment, when we had the thing in the sun versus in the shade, what do we see?
Oh, like more or less photoelectrons?
More or less photoelectrons. So what we got, the actual result, was greater current, so more electrons. What we've got in the particle model is like quantized model of light, is that each individual photon interacts with an individual electron, and that means that more electrons means more photons. So we're thinking about the brightness of light being more photons. When we think about the actual result, we have to think about the brightness of light. Like, as the light gets brighter, it means that the shower of photons is more intense, more photons per second. Frequency of light. One way that we often talk about frequency of light in everyday conversation is colour. What effect do we think that colour of light might have on the photoelectrons emitted, according to wave theory? So the actual result, we had to give different frequencies, different energy, but if we think about what we expected, we didn't expect that energy had any link to frequency. So what we were expecting was no effect. In fact, the actual result was that higher frequency light meant greater energy photoelectrons, and there was a minimum frequency below which no photoelectrons were emitted at all. And there's nothing in our wave theory that can explain why there's a minimum frequency, a threshold frequency, nor why it is that as the frequency increases, the energy of the electrons increases. And so how do we explain that? We had to go to Planck's idea of the energy of a photon being quantized and use the expression E equals HF for the energy carried by an individual photon. And the last thing is time delay. And it turns out that with wave theory, when we think about light as being like a wave washing up on a beach full of electrons, that energy of the wave is going to be spread roughly evenly, across all of the electrons. And that means it's going to take a while for any single electron to get enough energy to escape from the metal surface. What we see, in fact, though, is that instantly, as we shine the light on the metal, a current flows. We cannot measure any time delay at all, but we are expecting one in the order of like a couple of seconds. And once again, the only way that we can explain this is that a single photon with a whole lot of energy comes in and it gives up all of that energy to a single electron. And by doing so, that single electron gets enough energy to escape, even though all the ones around it haven't got enough energy to escape. So in the wave model, we were allowing all the electrons to absorb the energy of the incident light, whereas our actual result with no measurable time delay forces us to use a model that allows a single photon to interact with a single electron. Are we cool with that? So, how do we reconcile that with like the rest of our understanding of light.
Lights up stuff.
Lights stuff up, so something's lit up when the light reflects off it. Reflection, we can explain that with either a particle or a wave model. Like we can reflect a tennis ball off a wall, you just throw the tennis ball at the wall and it reflects off, right? And so, reflection we're quite happy, wave or particle. Something else we have to explain that light does.
Like interferes with itself.
Interference, yeah, good. Interference is one of those weird wave properties that we can't explain with particles. What's doubly fascinating though is that as well as needing to have wave-particle duality for light, as well as needing to sometimes think about light as a particle to explain how it behaves, turns out we also sometimes have to think about particles as being waves, because it turns out we can actually get particles to interfere with each other as well, which is mind-blowing. What else? Refraction. And refraction, we're definitely happy to explain that with a wave model, and I think that we can explain it with a particle model as well. If we think about particles slowing down as they move into a new medium, I think that we can explain it. What else? Diffraction. We can only explain diffraction with a wave model. We can't have particles that diffract. What about, is there anything you can think of that we can only explain with a particle model?
Powering on a Tesla with light.
What's that called again?
Photoelectric
Oh, the
effect.
photoelectric effect. And so, because we've got some phenomena that we can only explain with a particle model, and others that we can only explain with a wave model, we don't try to resolve this into being one or the other, but we keep the tension between them. Like the only way that we can happily live in a world with light is that we sometimes think about it as a wave, and we sometimes think about it as being a particle, depending on which phenomena we're trying to understand. It's just one of those tensions that we have to keep and be aware of how we're thinking about it when we come to solve any problem or explain any situation.